So from kind of the structure of what we've been talking about here, it should become clear that the right thing to talk about if you want to do counting is log C. Because the anomalous dimension equation was simple for log C. It was mu d by mu, or d by d log mu of log C is equal to something. That something on the right-hand side has an expansion in alpha, and we could include higher order terms in that expansion, but it would always be of that structure. So to talk about what terms we're summing, we can write the following schematic equation for different orders. So if we have alpha s to the k log to the k plus 1, which is this series I've just denoted, we'll call that leading log. And if we had some higher order term, like alpha s to the k log to the k, then that would be next leading log. And if we had more alphas than logs, then we call that next to next leading log. And the structure of the anomalous dimension equation always sort of guarantees that if you solve it for this log, that this is what the higher order terms would give you. Okay, so you should think of it that really with log counting is kind of like normal log counting, except for two caveats in this theory. You're doing it in the exponential. Okay, that's what taking the log did. And you sort of start out with one extra log, one more log than you're used to. But after that, it's kind of normal, because I'm summing here alpha times log, and I just increment for each alpha an extra log, and that's all the running coupling effects. When I go to next to the leading log, there'll, of course, be running coupling effects too, and other things that are causing this series. But it's down from this one because it doesn't have that enhanced log. And then this one is down again because it's got, again, one less log. Okay, so this is the kind of terms that you could sum by having higher order corrections in the anomalous dimensions. And for example, this cusp anomalous dimension is known at 3 loop orders. So certainly next leading log is well within the realm of things that people talk about. So let's ask that question. What coefficients, if we were to carry out this one loop calculation and we were to do higher loops, what coefficients do we need to compute? So remember the story when we were summing single log series was we would do like tree level matching, one loop anomalous dimension, then we do one loop matching, two loop anomalous dimension. What's the analog of that story here? So let's make a little table. So what information do we need at tree level? What information do we need at one loop? 2 loops, 3 loops. So for leading log, what we did is we put in tree level matching. And at one loop, we only actually took the information that came from the coefficient of the 1 over epsilon squared, which is the cusp anomalous dimension. Didn't need anything here. If you go to one higher order, it turns out that this is the story. To get this series, we would need the 2-loop cusp anomalous dimension, the 1-loop non-cusp, and still the tree level matching. So this next to leading log coefficient, this 5 CF, that's this 1 over epsilon. In our example, this was the 5 CF. And only when you get to next leading log, then the matching is 1 loop. You have the 2-loop regular anomalous dimension, and then the 1 over epsilon squared cusp anomalous dimension from 3 loop. So it's kind of like it's the usual story, but we have a kind of an enhanced, because of the double logarithms, we have an enhanced thing that we can talk about here, where we're not talking about the regular anomalous dimension, but this cusp anomalous dimension. Okay, so this is the information that you would need to go to higher orders. And this cusp anomalous dimension is actually a universal thing. So you can, given that it's been calculated, you can use it. And you don't have to recalculate it every time. These pieces you have to recalculate, these 1 over epsilons, general. Yeah?
Comment on the seeping, the arbitrariness of the boundary condition you chose?
Yeah, so if I hadn't chose that boundary condition, sure, let me write something. So the way that you could think about the RG is as follows, that you have C, and really what the RG is doing is determining some U that allows you to run C from some point to some other point, like that. So in this formula, mu naught is some scale that's of order omega, it doesn't have, or W. It doesn't have to be equal to W. It could be 2W, half W. And the way that you're thinking about this equation is you're going to do perturbation theory for this thing. And then in that perturbation theory, you'll have alpha, and you'll have like log squared of mu naught over W. But as long as you're saying mu naught's of order W, those aren't large logs. And this thing here, in this formulation, would have the double log series of alpha log squared of mu over mu naught. But then mu naught's of order W, and mu you can take much smaller, and that's the large logs. So for simplicity, I just took mu naught equal to W, but you could, everything I've said I could repeat, and the story would really be the same if I had just used an arbitrary mu naught. And the reason you actually want to use an arbitrary mu naught in general is that you want to do scale variation to think about uncertainties. And so the mu naught dependence, just like when we were talking about electroweak operators and electroweak Hamiltonian, the mu naught dependence cancels between these things here. But that cancellation is an order by order in alpha cancellation. There's no large logs associated with that cancellation. And so what it allows you to do is if you've truncated this to some fixed order and you've worked to some fixed order over there, then you can probe how much uncertainty you have by varying the mu naught. This mu here will get tied up with the mu in the operator. So we can talk more about where that mu goes later on. But at the level of this formula, it is in general the case that you would do it with an arbitrary mu naught and then only fix mu naught at the end. And you'd even vary mu naught to get an idea of how much uncertainty you have in your leading log calculation, because varying mu naught would probe the next term in this series here.
So when you say tree level matching,
yeah, I mean this C.
Not equal to 1.
That's right. I mean this guy here, right?
Right. And if you want to go to 1 or NNLL, you take 1.
Then you'd have this. That would have this term. Yeah. All right. Any other questions?